Hello and welcome back to Abstract Linear Algebra, the video series where we talk a lot about general linear maps and matrix decompositions. Indeed, in today's part 51, we will continue our discussion about the singular value decomposition. Here I will show you the whole calculation algorithm for it and also an explicit example. However, before we calculate these singular values for a given matrix, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget that a Steady membership is really worth it because you can download a lot of additional material for all the videos. For example, you find quizzes, exercises and my book about linear algebra. Okay, then I would say let's start with what we already know from the last videos about the singular value decomposition. Namely, we know it works for any rectangular matrix with complex entries. In particular, such a matrix always has singular values, which we denote by S1, S2 and so on. And we can always order them, and we know they are non-negative real numbers. We know that because they are connected to eigenvalues of a square matrix. More precisely, they come from the self-adjoint matrix A star A. In fact, one can easily show that these eigenvalues have to be non-negative, which means we can also take the square root of them. And then by definition, these are exactly the singular values of the matrix A. And there I should tell you that the order in this matrix product here does not matter so much. To see this, we can just look at the ordinary eigenvalue equation we have for this square matrix. This means we have an eigenvalue lambda and an eigenvector v. And now the idea is to simply multiply with the matrix A on both sides. Because then, as you can see, we have the combination A times v on both sides. This means this could be our new eigenvector u if it's a non-zero vector. And in fact we have that in the case that lambda, the eigenvalue, is not zero. Hence we get the eigenvalue equation for A star. And please note that the corresponding eigenvalue stayed exactly the same as the one for A star A. And since we can do the same steps the other way around, we actually get that the non-zero eigenvalues of A star A and A star coincide. So the conclusion is that for the definition of the singular values, it simply does not matter which order you choose here in the matrix product. The only thing that can change is how many zeros you have here at the end of the line. And there we already know that for the singular value decomposition, we only need the non-zero entries anyway. And now please recall, singular value decomposition means that A can be written as a matrix product. There we have two unitary matrices, one on the left and one on the right, and in the middle the sigma is a diagonal matrix. More precisely, it's rectangular like A, and it has only one diagonal with the singular values on it. And as we will see in this video, we can make it such that the singular values are on the diagonal in decreasing order. And indeed all other entries in this matrix are given by 0. So this is it. This is the singular value decomposition as we have already discussed it. And now we will discuss the whole algorithm for the construction of these two unitary matrices. And afterwards I will show you how this one works with an explicit example. Now for the algorithm, the key for the SVD, as we have already discussed in the last video, is in the eigenvectors of A star A or A star. And since both of them are normal matrices, we know that we can find an ONB consisting of eigenvectors. Therefore, the first steps in our algorithm are just about diagonalizing a square matrix. So first we calculate A star A and find all the eigenvalues of it. And since this is an n times n matrix, we already know that we can find exactly n eigenvalues. Which means if the multiplicity of an eigenvalue is higher than 1, we would just repeat it accordingly. Hence we always get the numbers lambda 1, lambda 2 until lambda n. Moreover, we can also choose the naming in such a way that we start with the largest one. Please note that the self-adjointness of the matrix implies that the eigenvalues have to be real numbers. Moreover, we know even more namely that they are greater or equal than 0. So we have the eigenvalues here, and in the next step we can go through the eigenvectors. And by the spectral theorem for normal matrices, we even know that we can find a whole O and B consisting of eigenvectors. This means you have to find the correct eigenvectors directions and you have to normalize them. So it's not so important how you do it, you just have to find the O and B in the end, and we already know it exists. Then the next step is quite easy, we just define the number lowercase r as the rank of A star A. And please note this is equivalent of saying how many of the eigenvalues lambda I are non-zero. Which also means if we go through the list, we will reach lambda with index r, and afterwards we only find zeros. This is important because in the next step, in the fourth step, we will have a for loop that goes through all the indices starting with 1 and ending with r. And then in the first step, we will define the singular values of our matrix A, which we call Sj. And as you already know, these are given by the square root of our positive eigenvalues. So we also find r positive singular values for our matrix A. Hence now we have the entries for our sigma matrix and we have the entries for our V matrix. So the only thing missing are the columns of our U matrix. So as in the last video, we will call them Uj. And there, as we have discussed it at the beginning, these are not eigenvectors of A star A, but rather of A star. So it's the other order, but as we have already seen, both things are connected by the matrix A. So if you multiply Vj with the matrix A, we get out an eigenvector for the other order. So this relation is quite nice, because it means we don't have to do the whole diagonalization of a square matrix again. However, we have a small problem, namely these vectors are not normalized in general. However, the last video showed us that it is normalized if we divide by the singular value Sj. So that's all we have to do, and then we already have some vectors for our U matrix. Okay, and now in the fifth step we make everything correct by saying that the larger indices for the singular values are just given by 0. This should be clear, but it should be mentioned because these numbers are also used later. So very well, and now as you know, for our U matrix we already have R vectors. And usually this is not enough because we need exactly M to fill out the U matrix. This means we could have two cases here. Either we have to add more vectors such that we have M and an O and B, or we have to top some 0 vectors that could be at the end of the list. Either way, it's always possible such that an O and B of Cm comes out. And there we finally have it. We have the two unitary matrices and we already know they lead to our singular value decomposition. So you see there is no magic involved here. It's just about finding the correct O and B's. And the mathematical justification for that is again the spectral theorem for normal matrices. And with that I would say we are finally ready for a nice example calculation. And I want to keep it simple, so let's take a 2 times 2 matrix. And the entries are 1, square root of 3 and 2. So in this case we have a square matrix, which means there is no difference between n and m, so everything is a little bit simpler. But still we can go through all the steps, and let's start with point 1, where we have to calculate A star A. Not a complicated calculation, we get 5, square root of 3, square root of 3 and 3. Moreover, the characteristic polynomial is also not so complicated, and I just tell you what we get. We get two eigenvalues, lambda 1 and lambda 2. The bigger one is 6 and the smaller one is 2. And then in step 2 we have to calculate eigenvectors, so we can go to the eigenspaces of A star A. And as you know, an eigenspace is simply given by a kernel. So if we subtract -6 on the diagonal, we get -1 and -3. And there, as always, we can just do some Gaussian elimination. And then we see that we can completely eliminate the second row. Hence, it's a one-dimensional kernel spanned by a single vector. And there you know, in general, we want to find an orthonormal basis of this span. So in this case, it's quite simple. We just have to normalize it. So we just have to divide by the length, and then we have our v1. So it's 1/2 times the vector square root of 3, 1. And now, not so surprising, we can do a similar thing with the second eigenspace. So there we have 3 and 1 on the diagonal. And then also easy to see, we just have -1 and the square root of 3 for the vector. Which means after normalizing it, we also have our v2. So in that case, we don't have any big problems with step 2. Then step 3 just tells us that we have two non-vanishing singular values of a. And these are just given by the square root, so we have the square root of 6 and the square root of 2. And now, as you might remember, we actually want to calculate the u vectors, which means we have to multiply v1 and v2 to the matrix A. More precisely, we have 1 divided by the first singular value, which is the square root of 6, times the matrix A times our first v vector. So it's a matrix vector multiplication, and what we get out is 1 divided by the square root of 2 times the vector 1 minus 1. And in a similar way, we also get u2. The only difference is that we have the second singular value and the second v vector. So what we get out is also 1 divided by the square root of 2 times 1, 1. So there we have it. These two vectors already form a basis of C2, so we don't need to extend it. Hence, in this case, there's nothing to do for step 5 and 6. And to finish step 7, we can just write down the whole singular value decomposition. So our U matrix has 1 divided by the square root of 2 in every entry. The only exception is the 1 minus sign here. And then we multiply this by our diagonal matrix in the middle. And as we know, this one has the singular values on the diagonal. And finally, the last matrix we have here is V star, so the transpose of V. Therefore, the only thing we have to do is to exchange rows and columns. And that's it. This is the whole singular value decomposition of A. And please note here, it's not the usual diagonalization we have for a square matrix. Simply because only non-negative entries are allowed on the diagonal, and also we need unitary matrices left and right. So this is the important fact you should remember, and now you also know the algorithm for this decomposition. Of course, it's more complicated if the matrices are bigger, but the same idea holds. Moreover, the singular value decomposition has a lot of advantages we can use in applications. So maybe let's talk about this with the next video. So I really hope I meet you there again, and have a nice day. Bye bye.